We're going to talk about characterizing different differential equations. We've already said that an nth order differential equation is just an equation that involves formulas, one formula equal to another formula, where those formulas just involve some variable. Here we're going to be using t for our variable, and some function y, and its derivatives up to the nth derivative of y. We can write that if we put all the formulas entirely on the left side of the equation, zeroing out the right side. You just move anything from the right side over to the left side, and you'll get some formula involving all of these things equal to 0. We'll call that a function of the nth derivative, the n minus first derivative, up to the first derivative, the original function, and our independent variable t. So that's a standard form for an nth order differential equation. If this function is linear in y prime, y double prime up to the nth derivative of y, then we say the differential equation is a linear nth order differential equation. What does it mean to be linear in these variables? Well, basically it means we can write it in the following way. We can write this equation as some function of t. Remember, it doesn't have to be a linear function of t. This function does not have to be linear in t. We'll call it a naught of t times this nth derivative of y plus some other function of t, a1 of t, times the n minus first derivative of y. And we keep going all the way up to the n minus some other function, a sub n minus 1 of t, times y prime plus a n of t times y, and all of that can equal some function of t, which we normally will just call g of t. Again, these functions a naught, a1 up to an don't have to be linear functions. They can be any complicated functions at all, as can g of t, but you can't have anything except a function of t multiplying any of the derivatives of y or y itself, nor can you like raise y sub n to some power. It just has to appear by itself multiplied by some function of t, and that's true for each of these functions. I think it will be clearest to look at some examples. So look at this equation here. Notice that we have y times y prime. That tells us that this equation is not linear. It's not a linear differential equation. Look at this next differential equation. You see we have x times y double prime. Here we're using x as our variable instead of t. We have x to the fifth e to the x times y prime. We have just a constant 4 times y equals x cubed. This is linear. Look at this third equation. In this third equation, we could rewrite it as y prime equals minus x, and you can see this is not linear because we have y multiplied by y prime. Notice that this differential equation is one which we solved in an earlier example and found all the solutions. We'll talk about those. We'll come back to this equation in the future when we talk about methods for solving equations like this. So what do you think about this fourth example? Is it linear or is it not linear? Well, again, this is not linear because we have this y squared here, t times y squared. Finally, what about this last equation, 4y double prime minus y equals 0? This is a linear differential equation. So all of this distinction is going to be very important, and you might ask, why is it so important to distinguish linear differential equations from other differential equations, which we call non-linear differential equations? And there are several things that make linear differential equations much nicer than nonlinear differential equations. First off, very importantly here, we have many methods for solving linear differential equations. Of course, there are plenty of methods for solving nonlinear differential equations as well, but we have much more general methods for solving linear differential equations. One of the things we're going to be talking about in our next lecture video is how to solve first-order linear differential equations, which we can do in great generality. What's the second reason they're so nice? Well, reason 2 is we have much more powerful existence and uniqueness theorems. And we haven't talked about those at all yet. I want to just give you a preview of this. This theorem that I'm writing down here will come up in section 2.4, which we'll get to in about a week. An existence and uniqueness theorem tells us how we can tell before we even solve a differential equation that there exists a solution. That's not always so obvious. In fact, in some differential equations, there might exist no solutions at all. And if there exists a solution, are there multiple solutions? Well, we've already seen in general you'll have multiple solutions for a differential equation, but if you add an initial condition, under many nice conditions, you'll actually get a unique solution. So, the first of our existence and uniqueness theorem says the following thing. If you have a linear differential equation, here we're talking about a first-order linear differential equation in this form, y prime plus p of ty equals g of t. P of t and g of t are just two arbitrary functions. But if these functions are continuous, if p and g are both continuous on some interval I, here we're talking about an open interval, and this open interval, it could be the interval minus infinity to infinity, or it could be array 0 to infinity. Any open interval, this theorem will still remain true. And you contain the point, and it kind of went off the edge of the slide, so I'll rewrite it here, t equals t naught. So if you have a point in this interval on which both p and t are continuous, then the claim is there will exist a unique function y, we'll call it y equals phi of t, which will satisfy this initial condition, satisfy this differential equation everywhere in that interval I, and it will also satisfy, let me state that again. There'll be a unique function, y equals phi of t, that will satisfy your differential equation along with an initial condition that you give. And this is a general form of an initial condition for a first-order differential equation. You tell me a point t naught, and you specify the value of our function y at t naught. Here, y naught is just an arbitrary number that you're specifying as the value you want your function to take at t naught. So, what's the result of this? If you have a first-order linear differential equation written in this standard form, notice in this standard form the coefficient here in the y prime is just 1. If you have that first-order differential equation written in the form, say a naught y prime, a naught of t, I'll call it y prime, plus a 1 of t y equals, I'll use capital G of t, then divide by a naught of t to get y prime plus a 1 of t over a naught of t, y equals G of t over a naught of t. And now it's in the standard form we need here for this theorem, where this is our p of t, and this is our function little g of t. So once we put in the standard form, as long as our coefficient functions p and g are continuous, and we have an initial condition at some point in that region where these functions are continuous, we're guaranteed a unique solution, and that solution to the initial value problem will be valid on the entire interval. Here's an example. The differential equation y prime plus e to the sine t times y equals log t is a horrible differential equation because this e to the sine t is a function that's very hard to deal with. But it still is a first-order linear differential equation. And when we look at these functions, e to the sine t and log t, these functions are both continuous on the ray from 0 to infinity. You can't have any bigger interval because log t, of course, is only defined on that interval 0 to infinity. So if we want to solve this differential equation with an initial condition that y of 1 equals 7, notice 1 is, of course, in our good interval, we're guaranteed that there'll be a solution that's valid on the entire interval. You're not going to be able to find a nice formula for it because you'll see, even though we have a method of solving such differential equations, you'll have to do things like integrate this e to the sine t, which won't give you nice formulas, but you at least know that there will have to exist a unique solution. Here's another example of a first-order linear differential equation, ty prime plus y equals 5. And you see the coefficients here are very nice. But we ask, can we guarantee a nice solution with the initial condition y of negative 1 equals 7? Well, we'll want to rewrite this differential equation in the form y prime plus 1 over t times y equals 5 over t. And you notice that these coefficient functions are continuous either on the interval minus infinity to 0 or 0 to infinity. They're continuous on both of these intervals. Since our initial value is obtained at -1, we're really interested in finding a solution that's valid on this interval. And our existence and uniqueness theorem tells us that there has to be a unique solution to this differential equation with this initial condition that's valid on the entire interval, in this case minus infinity to 0.